On April 13, 1940, the German destroyer designated Z12 faces a mathematical impossibility. She is boxed into a Norwegian fjord with fuel bunkers nearly dry. In the approaches, a Royal Navy force built around the battleship Warspite is pushing in, and the exit is shrinking by the minute. The captain of Z12 has choices, but none are clean: scuttle at the pier and try to save his crew, or cast off, run straight at 15-inch guns, and gamble on torpedoes before the channel turns into a killing ground. He chooses the second option. The order is given to raise steam, but the machinery inside Z12 is not standard destroyer engineering. She belongs to a German experiment in high-pressure steam, fast on paper, notoriously temperamental in service. When it worked, it squeezed remarkable power into a compact footprint. When it didn't, it punished crews with complexity, fragility, and almost no margin for error. And on this morning, the ship's machinery is becoming a liability. Erich Giese is critically short of fuel, and that shortage amplifies the chronic weaknesses of the type. German destroyers of this family were notorious for poor endurance, and a significant part of their fuel load often had to be retained low in the ship as ballast instead of being freely consumed. Accounts of the Narvik fighting also mention leaks, contaminated oil, and machinery trouble. No source preserves a clean, instrument-by-instrument failure chain, but the collision is plain. Low fuel, unforgiving high-pressure machinery, and a desperate tactical situation are meeting at the worst possible moment. The engineers struggle to raise and hold steam, and Z12 is no longer able to deliver the performance her designers promised. The destroyer casts off. She moves away from the pier, but she does not come out cleanly into action. By some accounts say Erich Giese could make well under her design 36 knots even on a good day, and the crisis in the harbor prevents her from using whatever speed she has left at the decisive moment. In the Narrows, every knot matters. The geography of the fjord still acts as the final lock on the prison. The British force holds the open water at the entrance, and the German ship must move toward a bottleneck instead of into maneuvering room. The ship moves past the harbor breakwater. The shapes of the British destroyers appear on the horizon, followed by the massive silhouette of the battleship. Down in the engine room, the situation degrades further. Multiple battle narratives agree on the broad outline, even if they do not preserve every internal mechanism in detail. Erich Giese does not have enough steam raised to join the action at once. When she later attempts to leave the harbor, Deutsche accounts report that her port engine seizes near the harbor mouth and leaves her almost dead in the water. The crew manages a temporary repair after roughly 10 minutes, but by then she can only limp ahead at about 12 knots. Too slow for a clean torpedo run, and too slow to live long in a fjord corridor under destroyer fire. For 7 decades, the silence of the harbor approach has replaced the thunder of the artillery. The destroyer Z12 lies on the seabed, or shrouded in the permanent twilight of the Arctic Circle. This is not a place for casual visitation. It demands planning, equipment, and restraint. The water is cold and dark, and Narvik is famously an ice-free port. Cold enough to slow some processes, but not a place of year-round near freezing seawater in the simple sense. The wreck is still a harsh environment, and the cold helps shape how the site ages compared with warmer tropical water. The position of the wreck tells the final chapter of her surface life. The hull lies on its port side. That fits a violent final roll, but it does not, by itself, prove exactly how the ship lost stability in her last minutes. In combat sinkings, flooding, damage, seabed slope, and the impact of settling can all leave a hull resting on its flank. What we can say is simpler: Z12 did not slip beneath the waves on an even keel. And the fjord's geometry still hangs over the ending. The location of the grave defines the tactical reality of the battle. This is the geography of the fjord trap. In open ocean naval warfare, a destroyer relies on speed and distance to survive against a battleship. She can turn, smoke, and run. Here, the landscape is a weapon. The fjord walls rise steeply from the water, creating a deep, narrow channel with few lateral escape routes. And yet the fjord is not a uniform abyss. Other ships in the Narvik fighting did run ashore or end up wrecked close to land. What matters is that the British force controlled the only exit. The German destroyer was fighting in a corridor that functioned like a rifled barrel. The wreck site has been visited before. Decades after the battle, divers went down to the hull. Some were not looking for history, they were looking for trophies. Items were pried loose, and the superstructure was left scarred, proof that for many years these wrecks were treated as scrapyards rather than monuments. However, the looters missed the most significant evidence. The hull remains structurally intact enough to map the damage. The bow section is recognizable, angling up from the silt. The stern section, though battered, still holds the shapes of the depth charge racks and the mine rails. But the most telling details are not the parts that are missing, but the parts that are bent. The propeller shafts and the rudders can hold clues. At roughly 220 to 230 feet, the wreck sits under a steady, crushing lid of water. Silt has built up around the lower portions of the hull as she lies on her port side. The exposed starboard side faces upward, softened by marine growth and years of immersion. What the wreck does not possess is an armor belt in the battleship sense. This was a destroyer with comparatively light hull plating, not an armored capital ship. To understand why Z12 sits here, one must look past the damage caused by the British shells. The bridge is smashed and the gun mounts are twisted. But a destroyer is a machine before it is a weapon, and the most important surviving clues point toward the machinery spaces now filled with water. Divers looking past the silent propellers are seeing the exterior of a ship whose mobility had already been compromised in the battle. What they are not seeing is a courtroom exhibit that can read out an exact shaft speed at the instant of impact. The wreck supports the broader historical record of mechanical failure. It does not by itself prove a minute-by-minute forensic script for the port and starboard engines. The Wagner boiler system is a masterpiece of theoretical physics and a disaster of practical engineering. In the design bureaus of the 1930s, German naval architects were obsessed with weight reduction. They believed that by increasing the pressure and temperature of the steam, they could shrink the size of the power plant while maintaining the output. The result was a machine that operated on the bleeding edge of thermodynamics. The standard Allied destroyers of this era often ran their boilers at a few hundred pounds per square inch. The Z12 belongs to a very different school of thought. In this German destroyer family, Wagner boilers are described around 1,000 pounds per square inch, roughly 70 atmospheres, while Benson boilers were higher, on the order of 1,565 pounds per square inch, around 110 atmospheres. Z12 herself is commonly described as a Benson boiler ship. This extreme pressure and temperature did not make the machinery magical. It made it demanding. The margin for error in these plants was narrow, especially under war conditions. The water inside the tubes had to be kept clean, and the plant demanded careful control. Contamination, leakage, or poor water chemistry could foul heat transfer surfaces and drive temperatures and stresses in the wrong direction. And because these were high-pressure systems, a serious failure in a boiler room could be catastrophic for the men inside. This sensitivity dictated the operational profile of the ship. The crew could not simply demand power, they had to manage it from a system that offered little forgiveness. On the morning of the sortie, the port engine of Z12 succumbs to that fragility. The historical record is clear about the outcome: loss of power on the port side at the worst possible moment. But it does not let us read a neat, instrument-by-instrument autopsy from the wreck. Whether the trigger was mechanical seizure, a cascade of control problems, or something as blunt as accumulated wear under bad fuel and bad luck, the result was the same: an immediate loss of motive power on the port side. This failure is not a simple mechanical stoppage. It forces a radical change in the ship's geometry of movement. A twin-screw destroyer steers by balancing the thrust of both propellers. When one shaft dies, the drag from the idle propeller acts like a sea anchor. The Z12 begins to pull hard to port. The helmsman must apply full opposite rudder just to keep the ship moving in a straight line. This induces drag, further bleeding off the limited speed generated by the surviving starboard engine. The telegraphs on the bridge are thrown to full ahead, but the machinery cannot obey. The ship is designed for 36 knots. She is struggling to maintain 12. This is the difference between a predator and prey. At 12 knots, the ship cannot throw her weight around the way a destroyer must. In a narrow fjord, slow speed means wider turns, fewer options, and more time under the enemy's guns. She becomes a stable, slow-moving platform, easier to track and punish in confined water. The digital resurrection of this failure sequence explains why the battle unfolded as it did. The Z12 did not maneuver aggressively because she physically could not. The port shaft was dead metal. The surviving engineers were likely fighting to keep the starboard boiler online, preventing a total blackout. They were not fighting the enemy, they were fighting the Wagner cycle. The ship was not defeated by superior tactics alone. She was betrayed by her own heart before the first British shell ever left the barrel. The paralysis of the port engine converted a daring breakout attempt into a static execution. A 15-inch naval shell can weigh around 1,920 pounds. It is a hardened projectile built for armored warships, not for the thin plating of a destroyer. That mismatch does raise the possibility of rounds passing clean through light structure, depending on fuse and shell type. But for Erich Giese, the public battle record does not let us prove a tidy sequence of over-penetration that spared the ship. The safer reading is simpler. Heavy shells from a battleship were devastating whether they burst inside after passing through or threw lethal fragments and shock through the hull. This ballistics failure on the part of the British battleship allows the German crew to continue firing their own guns for several minutes longer than the tactical situation should permit. However, the battlefield is not limited to heavy caliber fire. The British destroyers Bedouin and Punjabi are also engaging. Their main guns fire a 4.7-inch shell. This projectile is much lighter than a battleship round, but it is lethal to a destroyer at close range, especially in a fjord where hits come fast and escape routes are short. In accounts of the fight, Punjabi is badly damaged by gunfire, and smaller caliber hits are entirely capable of wrecking fire control, cutting steam lines and starting fires that doom a ship already in trouble. The damage accumulation becomes exponential. The structural integrity of the hull is compromised not by one single massive blow, but by dozens of smaller, internal detonations. The fires spread unchecked because the fire mains have been severed. The ship begins to settle. The buoyancy that kept her afloat is replaced by the weight of the flooding water. The port side list increases. The surviving crew members abandon their stations as the angle becomes too steep to stand on. The Z12 does not explode in a spectacular magazine detonation. She succumbs to a gradual loss of reserve buoyancy. The fires burn out the internal spaces, leaving a scorched metal husk that finally rolls over and slides beneath the surface. The violence of the surface action leaves the hull battered, with jagged entry wounds and twisted frames. But as the ship descends to the seabed, she takes with her a specific piece of bronze iconography that is bolted to her stern, a symbol that will survive the saltwater immersion better than the steel that carried it. In 2011, the curators of the Narvik War Museum face a difficult ethical trade-off. The wreck is widely treated as a war grave by custom, and diving and disturbance inside the harbor area is not a free-for-all. But earlier souvenir hunting had shown the site was vulnerable. Now the question becomes brutally practical. Do nothing and risk losing more, or work with the relevant owners and authorities to preserve what can be preserved for the public record? The decision is made to intervene. The target is the bronze eagle bolted to the stern of the destroyer. This operation is not a salvage of the ship itself, it is a surgical extraction of a specific component. The eagle weighs approximately 330 pounds. It is cast from high-quality bronze, an alloy of copper and tin that resists the corrosive effects of seawater far better than the steel hull it is attached to. While the ship around it has been slowly dissolving into iron oxide for 70 years, the eagle remains chemically stable. It is covered in marine growth, but the metal underneath is intact. The recovery team descends to the depth of 230 feet. This is beyond the limit of recreational diving. The divers must use mixed gas breathing systems to remain clear-headed at 7 atmospheres of pressure. The work is physically demanding. The eagle is secured to the steel plating of the stern with heavy bolts that have rusted into a solid mass. The divers cannot simply unscrew them. They must carefully cut through the mounting brackets without damaging the artifact or the surrounding hull structure. The physics of the lift requires precise calculation. The 330 pounds of bronze is heavy, but underwater the load changes because of displacement. Any lift method at this depth has a built-in hazard. Gas expands as it rises, and a mismanaged lift can turn violent. The team plans for a controlled recovery, using professional procedures to keep the artifact and the divers safe. When the eagle breaks the surface, the operation shifts instantly from recovery to chemistry. For decades, the bronze has been in equilibrium with salt water, but chlorides can lodge in corrosion layers and pores. When chloride-contaminated copper alloys are exposed to air and moisture, chemical reactions can generate hydrochloric acid and drive the cycle conservators call bronze disease. The immediate priority is simple: keep the artifact wet and stable, and transfer it into controlled conservation handling so chlorides can be managed before drying and oxygen exposure accelerate damage. The ship's bell is the traditional voice of a vessel for Z12, and that voice was stolen in the 1960s and lost to the black market of nautical antiquities. It likely sits in a private collection, silent and undocumented. In its place, the 330-pound bronze eagle recovered in 2011 serves as the primary witness to the destruction of the destroyer. It stands today in the Narvik War Museum, preserved in a controlled environment that arrests the chemical decay of the metal. The artifact itself is a dense, heavy object. It is not merely decorative, it is industrial art that survived forces that tore the steel hull apart. In the museum light, that survival becomes a quiet contrast with the wreck still collapsing in the fjord. And the contrast points to the deeper tragedy of the type 1934 Alpha-class destroyers, ambitious materials and ambitious speed, married to concepts too fragile to absorb real war. The analysis of Z12 often suffers from a phenomenon known as target fixation. In a tactical sense, target fixation occurs when a gunner or a pilot becomes so focused on a specific threat that they lose situational awareness of the broader environment. In a historical sense, this battle is often told the same way. The narrative locks onto the battleship Warspite, 15-inch shells, the drama of the final torpedo run, and lets the mechanical story fade. But the technical reality is the point. The Z12 was not merely overpowered by a superior enemy. She was compromised by her own engineering. The decision to prioritize speed and weight reduction over reliability created a glass engine, enormous output on paper, and little forgiveness in the friction of actual warfare. The legacy of the Z12 is not defined by the shell holes that punctured her hull. It is defined by the telegraphs that signaled for a speed the engines could not deliver. The German Naval Command gambled that the high-pressure steam technology would provide a tactical advantage. The wreck at the bottom of the fjord is the physical proof that this gamble failed. The port shaft seized because the tolerance for error was too narrow for the conditions of the Arctic campaign. The fuel systems failed because the feed pumps could not handle the sloshing of the dregs in the tanks. The recovered Eagle is a static object, but it represents a dynamic failure. It was bolted to a ship that was designed to be the fastest in the world, yet it went into its final battle moving at the speed of a coal barge. The museum display strips away the noise of the battle and leaves only the silent, heavy metal reality. The destroyer was a fragile machine sent into a heavy industrial environment. In the end, the wreck of Z12 remains a protected site. Divers do visit the hull, but in and around the harbor the rules matter: permits, limits, wherein the reality that these wrecks are also graves. They swim past the twisted davits and the empty gun mounts. They hover over the open hatches of the engine room, peering into the dark spaces where the steam lines once hissed at extreme pressure. The ship is slowly collapsing under its own weight, the decks folding down as the bulkheads rust through. But the story is locked in. It is a lesson in the limits of optimization. The engineers drove steam to the edge of what metal and water would tolerate, and in that fjord the bill came due.